All right, so starting off with a few multiple choice questions, we are given a vector field, and we know that P is a point somewhere on the surface, x equals 7, n is a normal vector, and then the question is about this quantity right here. So this del operator cross F, that's better known as curl, and then we should get a vector out, and then it'd like us to dot product it with the normal vector here in order to get like a number. And the question is that number positive, negative, 0, not enough information to tell, and none of the above is kind of a silly answer there, but fine. All right, so the big thing is to calculate out our curl. So we learn, and this is a 16.5 style question here. We have our i's, j's, and k's. This del operator is all of our partial derivative information. So a partial derivative with respect to x, then with respect to y, then with respect to z. And then we need to put in our vector field. So it looks like we have 3x cubed, 5y to the 5th, and then negative 2z to the negative 2 plus x. Whenever we take a cross product, we're going to have stuff with i's minus stuff with j's plus stuff with k's. I'm not sure if I've given myself enough room or not, but we'll see. Crossing off that first row and first column, let's see, we need to take a partial derivative with respect to y of stuff that doesn't have any y's in it, and a partial derivative with respect to z of stuff that doesn't have any z's in it. Next up, crossing off that first row and second column, a partial derivative with respect to x of this negative 2z to the negative 2 plus x. So it's going to be a 1 there. And then a partial derivative with respect to z of stuff that doesn't have any z's. So that's going to be minus 0. And then finally, we need to cross off that first row and third column. And, looking at this, it's going to be 0 minus 0 again. So our vector happens to be 0, negative 1, 0. Now, we want to dot product this with a normal vector. So this is kind of a little bit of, of stuff that we used to do really before chapter 15. We talked about surfaces and normal vectors and all that sort of stuff. And so we know that there's a couple of different formulas that give us normal vectors at this point, right? In particular, this is quite a nice surface, all things considered. And so there are many different ways, I suppose, that you could get normal vectors for this surface. Of course, maybe most complicated, you could try to parameterize it or something like this and then do a cross product of tangent vectors. That would be very, very extreme. But one good way, for instance, that we saw in 14.6 is that if you have a function with all of your variables on one side, and you have that equal to a constant on the other side, then can anyone tell me what is going to be a normal vector in such a situation? What can we do in order to find a normal vector? Anyone remember? Yeah, you have a guess? Yeah, exactly. Yeah, so it was the gradient, right? So this was the main use of the gradient back in 14.6. So if and again, I do have all of my variables on one side. It's kind of silly because it's just x. And I have a constant on the other side. And so if I take my gradient, right, here, this is going to be a partial derivative with respect to x. Well, that's going to be 1. A partial derivative with respect to y, 0. And a partial derivative with respect to z, 0, right? Because again, on that left-hand side where all of our variables are, there's just a single x, right? And so this is going to be a normal vector. Of course, right, we could have actually figured this out as well just by kind of thinking about this is a very simple plane here. And if you remember, kind of you can do a plus or a minus. But either way, when you do a dot product, whether that's plus or minus, with what we have right here, right, there's just not, any alignment here. So you're going to have 1 or negative 1 times 0, 0 times negative 1, and 0 times 0. Add those all up, and no matter what, you're getting 0. So the answer here is 0. And although this is a little bit of a arbitrary calculation right here, that this dot product with a normal vector, at this point, my claim is that later on in 16.8, actually this will become very popular, I guess. This will be a common calculation that we're doing. And so this is kind of a little bit of a peeking under the curtain sort of deal as far as where we're headed next. So anyway, that's our first problem here. Next one, it talks about the same vector field, but now the setup, this is a velocity field of a flowing gas. And we want to know at which point is the gas being compressed. So we need to remember something about, well, this compression and kind of how this came up. So you may remember, right, if the divergence of your F was equal to 0, that this was incompressible, right? So maybe this is something that, a definition that kind of related to this. We also said that if the divergence of F was greater than 0, then there was more expansion going on than compression at this point, right? If there was more going out than coming in. There was more expansion than compression. And so all that to say, what we're very much interested in this particular case is when is the divergence less than 0? Because in that case, there's going to be more coming in. There's going to be, with the velocity field, right? There's going to be more compression. There's more going in than there is going out. And so we are looking for, these are the words that maybe explain that we want a divergence being negative. And so, okay, well, I can calculate out a divergence. That's not too bad. So divergence of F. Remember, we go along and technically we're doing a dot product with our del operator. So we need to take a partial derivative with respect to x of our first component. That's going to be 9x squared. We need to take a partial derivative with respect to y of our second component. That's going to be 25y. It's a really bad y. There we go. To the fourth. And then finally, we need to take a z derivative of our third component. So -2 times -2 is going to be +4, z to the negative third power. And we're hoping that one of these points, that when I plug it in, right, we'll end up getting a negative divergence. And so maybe the first thing, right, if I go ahead and I plug in 0, 0, 0, we're going to get 0 plus 0 plus 4 times 0 to the negative third. If you try to plug that into your calculator, you know, technically what's going on here is that this is division by 0 to the third power. So you're dividing by 0. I don't know what this is, but it's not negative, right? It's not positive, it's not negative, it's undefined. And so, nope, this isn't it. How about if I was to plug in my point at B, right? So at 0, 0, -1. So 0 for x, 0 for y, and then -1 everywhere I see a z, right? So that's going to be, again, division by -1 cubed. So -1 times -1 times -1 is -1. And you multiply that by 4 there. So this is going to be equal to -4. So indeed, our divergence at this point is negative. That means that there's compression going on here. And so our answer is going to be B. Of course, you can check the other ones if you have extra time on your exam or whatnot and verify that both C and D result in a positive answer. So B is the only correct result. But again, once I find an answer that works, I wouldn't necessarily spend the time plugging in C and D unless if I had time to kill, right? And I just wanted to double check and make sure that I have the correct result. All right, any questions on either 1 or 2 here? Again, this is 16.5, a bit of review here. All right, well then, why don't we go ahead and move into more standard response style questions. So here's a situation where we have a density function, right? So I fill an enclosed volume of a solid with oil and vinegar, which together seem to have a density function of 1 over x squared plus y squared plus z squared in grams per cubic meter. And my question is, how much does the substance weigh overall? And it looks like I'm filling this thing that's inside of rho equals 4 cosine phi. So I have a little bit of conflicting information here, right? I have some stuff given to me in spherical coordinates, it seems, and some stuff given to me in Cartesian coordinates. However, the stuff that's given to me in Cartesian coordinates, x squared plus y squared plus z squared in the denominator, seems like it'd be pretty nice to convert into spherical. So all things considered, even though this says I don't have to necessarily do it in spherical, it's much easier, I think, to convert from Cartesian into spherical than the other direction. And so I'm interested in setting up, I guess all of this is really, a reminder of if you're interested in mass from density, you need to do a double or triple integral. In this case, because we have a 3-variable function here, we're going to need to do a triple integral, one for x, one for y, one for z, and overall this should give us the total mass. We also saw situations, and in fact my next problem here for us is the same sort of question, but now in a 2-dimensional setup, right? We have a thin plate, a lamina, right? And we're interested in finding the mass of a 2-variable density function, right? So we have seen this situation kind of for both 2 variables and 3 variables. So in my case, in order to get the total mass of this oil and vinegar combination, we want to do a triple integral of my density function. The surface that's given to us is this rho equals 4 cosine phi. And so once I've decided that I'm going to convert this into spherical, remember there's many different ways that we can evaluate out a triple integral, right? I mean, we could do an integral with respect to z first, and then maybe y and x next, or we could do maybe x first, then y and z next, or there's all those different Cartesian ways, but then we also can decide to convert this to either cylindrical or spherical. So really there's like 5 different ways, even more than that. So once I decide to convert to spherical, really my order of operations is, I think it's maybe easiest to convert the function. The next easiest thing to get, to maximize partial credit is to make sure to include the Jacobian. So this rho squared sine phi. And then the most difficult thing I would say is to set up the bounds. And so I usually save that for last. Now I notice that for my surfaces given, there's only one. It's this 4 cosine phi. And maybe the first thing that I notice about this is that it's independent with respect to theta. There are no thetas in it whatsoever. And so in such cases, right, we've talked about many times, that if you don't have any restrictions on theta, and you want to get all of your points, well, that means you're going to allow theta to range from 0 to 2 pi. So I could set up those theta bounds pretty confidently without a whole lot of work. If you were guessing, right, and you wanted to resist the urge to draw a picture, right, I suspect most people would guess this: 0 to 4 cosine phi, 0 to pi, 0 to 2 pi. I think that this would be a common guess. And of those 6 different bounds that I've written here, 5 of them are correct. There's only one that's incorrect. Can maybe anyone tell me which of my bounds that I've written here is incorrect? So I have a vote online here that the phi bound instead of pi should be pi over 2. This is a true statement. So the incorrect thing here is that this should be pi over 2. There are 2 different ways that we can see that that should be pi over 2. A graphical way, right, where we could give in and actually graph the surface, right, or an algebraic way. So the graphical way, and what we did a lot in our spherical setups, right, is that because this doesn't rely on theta, is that quite often when we were sketching these things, we'd graph them first in the RZ half plane, and then we could spin them around the z-axis in order to get the full 3D picture. And so in these cases, right, we would say, what if phi was equal to 0? That is, we're pointing straight up towards the positive z-axis. So if I was to plug in a phi value of 0 into my equation, we'd have 4 cosine 0. Cosine of 0 is 1, so this would be 4 times 1, which is, of course, 4. We'd be going out 4. Then we could say, what happens if phi equals pi over 6, or phi equals pi over 4, or phi equals pi over 3, or phi equals pi over 2, right? And we could keep on plugging in these different phi values into our surface equation. And that tells us how many steps away from the origin we need to walk, right? And so, for instance, if I plugged in pi over 6 into my phi, we'd get 4 times cosine of pi over 6 is root 3 over 2. And your calculator, right, you can plug this in. Maybe it's like 3.6 or something like this, right? It'll, of course, give you a very good estimate. And so that means I need to move out 3.6 steps. So maybe something like this. And then, when I plug in, for instance, pi over 4, right, that'll tell me how many steps I need to walk away from my origin. And then pi over 3, that one's nice because cosine of pi over 3 is 1/2. So 4 times 1/2 would be 2 steps away from the origin. And then cosine of pi over 2 is 0. And so you start to sketch this picture that looks like this. And if you plug in a phi value of 2 pi over 3, the cosine of 2 pi over 3, your calculator will tell you, is -1/2. So that means that your rho value is going to be 4 times cosine of 2 pi over 3. So again, that's -1/2. You're going to get -2. This is the algebraic way of kind of thinking about this here, is that we're ending up with a rho value that's negative. And remember, in our class, the r values and the rho values, these radiuses should always be positive. And so if you can figure out when this equals 0, when it's making this transition between the positives and the negatives, right, this is going to be where you want to stop. Otherwise, you're going to start double counting your points. And so algebraically, cosine is positive between 0 and pi over 2. And so that's the algebraic way that you could see that the bounds here should be 0 to pi over 2. Graphically, again, we've now done the graph here. We can spin this around. And graphically, you can see that this picture, right, it doesn't intersect. When you graph phi equals 2 pi over 3 or anything larger, right, there's not a picture down there. So you never intersect with your region. So this would be the graphical way to see that it shouldn't go from 0 to pi, but 0 to pi over 2. However, all that to say, right, if you were to do this from 0 to pi, and let's suppose that this is a 10-point problem, right? And you guessed and you didn't catch that it was supposed to be from 0 to pi over 2 and you did 0 to pi, it's still very possible that you're getting 7 or 8 out of those 10 points. You're still getting the majority of points. And so it's much better to guess and be wrong and kind of make some progress and try to maximize your partial credit than it is to say, I don't know, and kind of just stop trying and move on to something else, right? So, I mean, certainly it's better to make a guess and do the work with a wrong value than it is to just not write anything because you're not 100% sure. And so I just want to emphasize, try to maximize your partial credit here. Okay, well, we can see that there's a little bit of cancellation. We have our bounds set up, so we're now moving into the evaluation portion. I notice that none of this stuff here has any thetas. So I can rip off my theta integral, just 1 d theta, and evaluate that. The integral of 1 d theta from 0 to 2 pi is going to be 2 pi. This just enables me to do kind of 2 calculations in 1 step, rather than kind of, right, it just saves me 1 line. If you don't want to do this and you would rather write out the extra line, by all means. Now you can't rip apart these inner 2 because, right, here you have phis in your bounds, right? And so you can't separate these ones, maybe like we sometimes like to. And so I do need to evaluate this. It's a rho integral. All my rho's have canceled though. So I mean, when I integrate with respect to rho, this is my constant phi, and I integrate with respect to rho, it might as well be like, when you integrate 5, you get 5x, right? So this is constant. You're integrating with respect to rho, so you get whatever that constant is times rho. And then we need to evaluate that from 0 to 4 cosine phi. Those are our bounds for rho. So again, I was able to do kind of 2 integrals in 1 step, save me a little bit of time. All right, now let's go ahead and plug in our bounds formally here. All right, we're going to have 4 sine phi cosine phi d phi. Of course, when you plug in 0 into our rho there, we're just going to subtract away 0. We could take out this 4 and we'd have 8 pi outside altogether. And then we need to be able to evaluate out this sine times cosine. This is a small u substitution, which of course you can do a little bit of guess and check, right? So if u is equal to sine here, then du is cosine. So when I integrate this, I'm going to have 1/2 u squared. And so I should get something like this. Of course, you can double check, right? If I take the derivative of this, I should get back to where I started. That's how you check if this is the true antiderivative. So again, you're certainly allowed to do this, and I've tried to push you guys throughout the semester to kind of get good at your u substitution and being able to do it this fast. Of course, if you're not there yet, you're still a little bit hesitant, right? Take the extra line or two. Really pull it off to the side. Say u is equal to sine of phi, du is equal to cosine of phi d phi, right? And it's better to be correct, especially on exams, than it is to be fast, right? So if you have gotten to this point and you're confident, then by all means, if you're not quite there yet, pull it aside, take the extra line or two, and get the question right. All right, well, the 1/2 can come out, cancel with the 8 pi there a little bit to get 4 pi. Sine squared at pi over 2, well, sine of pi over 2 is 1, and sine of 0 is 0. Of course, when you square those, they're not very interesting. And so you just get to that 1 minus 0 times our 4 pi. That's going to be 4 pi. If you go back and you look at our units, I don't even know why I included units for this one, but assuming that x, y, and z are all in meters, our function was in grams per cubic meter. So this would be 4 pi grams. This is going to be the mass in total. Of course, in our math class here, we're not very picky about units like they are in some of the other science classes. Most of our problems don't even have units. All right, any questions on this first standard response style question here? I think this is a spherical style problem that is, appropriate to be done in a time setting. All right, well, let's go ahead and move on then. And we will do another sort of mass from density style question. However, this one, you can see that our density function only has 2 variables, x's and y's. In fact, as you read the entire problem, you never see a z, right? This is really an indication that you're doing a double integral rather than a triple integral, right? And so we're interested in, again, finding a mass. But now our density function is a 2-variable density function, right? Oops, it's a bad sigma. And so we could go ahead and substitute that in. And again, when it comes to double integrals, we have 3 different ways that we could evaluate these, right? We could do a y integral first and then x. We could do an x integral first and then y. Or we could convert this into polar, right? And we could decide that we're going to try it out in polar. What this all does, which one of these we choose is largely dependent on the region, right? And so all of this is given to us in Cartesian. And so I'd like to maybe sketch out and see what this region actually looks like. So it has mentioned that we have an ellipse. Of course, maybe we can remember from 12.6, and even without the statement that this is an ellipse, right, we could identify it just because there's x squared and y squared, and they're both positive. And then we also have a parabola, right? And again, even if it didn't tell us that, we could get from the sketch that this is going to be a parabola. So when it comes to ellipses, if I want a moderately good picture for what my ellipse looks like, usually I try to find the vertices, right? I try to find 4 points here, and from that I can draw my ellipse pretty well. So I might start off with x equals 0 into my ellipse equation and solve what y values make that true. So in this case, if I was to divide by 4, I would get y squared is equal to 3. So that's going to be y is equal to plus or minus root 3. And so this is right around 1.8-ish. So maybe these points would be x equals 0, y equals somewhere between 1 and 2, a little bit closer to 2. Likewise, if I was to do y equals 0, again, just getting my vertices here, and plug that in, I would get x squared is equal to root 12. Oh, sorry, I'm ahead of myself. X squared is equal to 12. So x is equal to plus or minus root 12. So again, I'm just plugging these into my ellipse equation. This time, everywhere I see a y, I'm plugging in 0. And I know that root 12 is somewhere between root 9 and root 16, right? But of course, your calculators will give you an excellent result for that. So I know that this is somewhere between 3 and 4. And so a decent picture for my ellipse looks something like this. Now my other curve here, my other equation given to me is for a parabola, x equals 4y squared. And again, maybe there's some of you out there who can just see this equation now and you know that this is a parabola going off to the right because it's x equals sort of deal. But for anyone who's still a bit hesitant, right, you can use this point plotting method. And so we could plug in things like y equals 0 or y equals 1 or y equals -1, right? And see what x values correspond to that. So if I plug in y equals 0 into my parabola, right, I get x equals 0. So that means that the point y equals 0, x equals 0, that's the origin, is on my parabola. If I plug in y equals 1, well, that's going to be 4y squared, so that's going to be x equals 4. So at height 1, I'm going to have, right, y equals 1, x equals 4. I would normally write that 4, 1 as an ordered pair. That's going to be over there. And at y equals -1, again, I'm going to have 4 times -1 squared. -1 squared is 1, so that's going to be 4 times 1 is 4. And so down here, at y equals -1, we have an x value of 4. So that means that my parabola is going to look something like this. Let's reread the question, right? Find the mass of the thin plate occupying the smaller region cut from these two curves. So the smaller region is going to be this one right here. Looking at this region here, this does not scream to me polar. It does not look like a circle or a part of a circle, right? This is a very, I mean, the parabola is certainly coming into play quite a lot. And the ellipse isn't even a circle, right? I mean, it's kind of a stretched out thing. But yeah, none of this is really screaming polar to me. So I need to either decide probably to integrate with respect to x or with respect to y first. One of these is much, much better than the other. Can anyone tell me which one is much, much better? We'll go down here this time. X. So I agree that integrating with respect to x first is much, much better than integrating with respect to y. Why I say that and why I believe it's much, much better is because if you decided to integrate with respect to y first, you would actually have to split this up into two different integrals, because how you enter into your region would sometimes be along this bottom portion of a parabola, which by the way would have some square root in it. But other times it would be along this bottom portion of the ellipse. So depending on how far you are left and right, sometimes you would enter in through one curve and sometimes you would enter in through a different. And so that means that you would need to really break up your integral into two pieces. And now you'd have to figure out when do these things intersect and where's that break point and all this sort of stuff. So this is a huge pain if you try to integrate it with respect to y. On the other hand, if you integrate with respect to x, you always enter in the left-hand side, right, is always this parabola, and you always exit through the ellipse. This is also emphasized, at least in the parabola equation, because it solved x equals. So if you want to know kind of what is the algebraic kind of hint that integrating with respect to x is going to be better, is because you see an x equals. If you saw y equals, right, it may be better to integrate with respect to y first. So now I've decided that I'm going to integrate with respect to x first, then with respect to y. I'm going to be entering in through my parabola. So this 4y squared, my x bound, x equals 4y squared. and I'm going to be exiting through this ellipse. But again, it needs to be an x bound, so I need to solve my ellipse for x equals. So if I spend a little bit of time off to the side here, solving this x equals, I'm going to have a plus and a minus. One corresponding to all the parts of my ellipse where I have negative x values. So right, the negative square root is going to be all this stuff over here where I have negative x values. And all of the positive stuff is going to be over here where I have positive x values. And so you can see that the only one that I'm actually exiting out of, the only one that I'm interested in is where we have the positive square root. And so I'm going to be exiting through the positive square root of 12 minus 4y squared. Oops. And now lastly, I need to set up my y bounds. This is going to correspond to the smallest and largest values of y that are included in my region. And so it's going to be whatever this point is down here is my smallest y value. And whatever this point is up here is going to be my largest y value. So you can see that ultimately I need to know where these things intersect. Algebraically, that means we need to set these equal to one another or kind of do some substitution here. And again, we're interested in solving for y. And so, however, I do think it's a little bit easier to maybe get x first. And so if I was looking at this and I'm setting up and trying to solve this system of equations, I would probably plug this in everywhere I see this 4y squared, right? I see that there's 4y squared is equivalent to x. And so if I substitute that in, I would get x squared plus x is equal to 12. With this, I can rearrange and I can factor. And this tells me that the x value is either going to be -4 or 3. Well, I know I can look at the intersection, right? One of this is going to be extraneous and one of it's not, right? The x value is clearly positive. It's clearly to the right of the origin. And so x equals 3 is the one that I'm interested in. And so if I want to know the y value, then I can plug this in into either one of these. So of course, I like the parabola a little bit more. So I'm going to go ahead and plug that in. So again, the parabola equation was x equals 4y squared. And so I'm going to get 3/4 is equal to y squared. And so therefore y should be equal to plus or minus root 3, and the square root of 4 is just 2. And so this upper one here is the positive y value, root 3 over 2. And down here we have the negative value, root 3 over 2, right? These are my y values. So negative root 3 over 2 to positive root 3 over 2. And then a question of what does the -4 mean on the graph? The -4 just comes from, let's see, if we plugged in our 4y squared here in for x. I don't have a good interpretation of what that -4 means on the graph. It's just an extraneous solution. So I mean, in the same way that you used to solve these in your algebra days and you got kind of nonsense solutions, that's what's happening here. Yeah, this -4 isn't even where, I mean, the ellipse doesn't reach a value of x equals -4, right? X equals -4 is out here. So sadly, I don't have a good reason for why that shows up. Just sometimes, yeah, extraneous solutions do that. All right, we have the setup done. I would probably say, if this was a 10-point problem or so, I would say that probably the setup is probably guess at least 6 or 7 of the points here. So usually the setup is the majority of the points. Of course, once you leave our class and you have, you know, sophisticated computer programs and all this sort of stuff, right, they can evaluate this for you. What we really need is, right, figuring out what should be these bounds. That's the important thing for us humans to still be able to do, set up the equation, and then a computer can evaluate this for us later. Let's go ahead though and finish up our evaluation. It's nice to get a good final answer here. So when I integrate this with respect to x first, oops, you can see we're going to have an x squared. That's going to be nice. It's going to kind of help save us from some of these square roots and stuff. Let's go ahead and bring out this 5/2. Why not? And so when I plug in into my x squared here, the square root, that's going to nicely cancel. And we're just going to get 12 minus 4y squared, what was inside of our square root. And then I need to subtract away, and I need to plug in my 4y squared, again, into x squared. So 4y squared into my x squared. This one doesn't have a square root to nicely cancel. Well, such is life. Now we need to integrate one more time. Let's see, 4 squared is going to be 16. And y squared squared is going to be y to the 4th. So when I integrate that, that's going to become y to the 5th. So I need to divide by 5. So my final answer would look like this. I would do them kind of term by term. So first, for the 12y, I would do root 3 over 2 minus a negative root 3 over 2. Then for the negative 4/3 y cubed, well, negative 4/3, and I mean, you could just literally plug this in cubed, sort of deal, but this root 3, if I was to cube that, that would be the same thing as root 27. And if I was to cube that 2 down there, right, 2 cubed is going to be 8. Minus a negative, when you cube a negative, it stays negative. So minus a negative is going to be positive there. And root 27 divided by 8. So if you think that's simpler, you can do it. Or you could just leave that as literally root 3 over 2 and cube that. And then finally, negative 16/5. And now it's getting fun with things raised to the 5th power. Correct me if I'm wrong, but I believe 3 raised to the 5th power, 243. And I believe 2 to the 5th power is 32. At this point, obviously, you see some common denominators here. You could start to simplify and whatnot even more. You have to figure out how much do you want to simplify versus when do you want to just plug this thing into your calculator, right? Eventually, you're going to plug this into your calculator. You're going to get a decimal to 3 decimal places, and that would be what you would input into D2L. So I would say maybe here's a fine time, or maybe you can take one more line to simplify. 16 and this 32 is going to nicely cancel. This 4 and these 8s will nicely cancel, right? So there is more cancellation that can be done. All right. Any questions on this one? I see there's something in the Q&A. Someone asked, can you suggest a way or sources to practice true-false questions, which ask a small concept from a chapter? Yeah, I can try, but you've correctly identified that, I mean, these true-false questions can be quite conceptual. And so I have included here at the end of class, and maybe now is a good time to jump to those just because we do have 10 minutes left. We could look at some of these true-false style questions. I would also maybe emphasize as an answer to this question, then I will go back and see if anyone has any other questions about this double integral problem. I just wanted to say that, yeah, so the textbook has some true-false questions at the end of each chapter. So there's a true-false concepts quiz or something like this at the end of each chapter. Of course, if you don't have the textbook, the MSU library does, and they even do the digital checkouts and stuff like this. Also, you may be able to Google search and find a portion of the textbook online, stuff like this. So anyway, I hope that you have the textbook, but if you don't, there are other options. I would also say that this would be a good thing to kind of go back through the quizzes and make sure to take special note of the true-false questions that have been asked on the quizzes. That would be another good thing to be doing as well. All right. Before we jump to the true-false stuff here, so this one is about the fundamental theorem of line integrals. It's another 16.5 style question. I will post the answer to this by 3 o'clock today. I invite you to try this one again on your own. Any questions about this one before we formally move on? All right. Well, so yeah, let's use our remaining time then to do some true-false style questions. So we have a double integral, and the question is this quantity here less than or equal to 9? And then we have a couple of statements here about curl and divergence. One asks if the curl obeys some addition law. So the curl of f plus g, is that the same thing as the curl of f plus the curl of g? And then the question is, how important is this div for number 8 here? If the divergence of f is equal to the divergence of g, does that mean that the vector fields f and g must have been the same? There was kind of thinking back to our 15.2, when we first came up with these double integrals, there was one theorem that we had that had an inequality in it. It's maybe not surprising that this theorem is the important one for this problem, right? After all, we see an inequality. If you were to try to just evaluate this and get an answer, this is very difficult, right? We have this x squared times sine of x squared, right? Use substitutions, all these sorts of things, right? It'd be very difficult in order to try to evaluate this as it stands, but luckily we don't have to, right? We only are asked, is this quantity less than or equal to 9? The other thing that kind of is pushing me towards this direction here is that we have natural inequalities for sine, right? So we know that sine of whatever's on the inside is always between 1 and -1. So in this case, we happen to have, right, x squared plus y squared on the inside. But sine, no matter what you input into it, is always bounded between -1 and 1. And so we can create the function that we're interested in then by just multiplying x squared plus root y into the middle here. And of course, if you don't want to break your inequality, you should do the same thing on all sides. Now remember, so long as you multiply by a positive number, that the inequality is maintained. So x squared is positive, and then we have plus the positive square root of y, which is also positive. So this will be positive, so the inequality is maintained. And then the one theorem that we have when it comes to inequalities and double integrals is that double integrals maintain inequalities. So that is, if you do a double integral on all 3 sides, that it doesn't break your inequalities. So I guess at this point, right, we're only interested in this thing larger than our function here, this x squared plus root y times sine of x squared y squared. And so I become very interested in this much, much simpler integral here, right? I can now start to set up my bounds again. So this is from 1 to 4, 0 to 1. 1 to 4, 0 to 1. Again, integrating with respect to x first and then with respect to y. This thing on the right-hand side is much easier to evaluate. I think when I do this, in the interest of time, maybe I'll skip this for the time being. But if I recall correctly, when I did this before class, I think I get like between 6 and 7 or something like this. So the answer here ends up being between like 6 or 7. I can include this in my post by 3 o'clock today. But whatever this answer is certainly less than 9. And so because, right, we know that this simpler integral is less than 9, then certainly, right, the more complicated thing is less than 9. So this is sort of like a squeeze theorem sort of deal. So this one is true. Complicated though. 7 and 8 are much less complicated. So for problem number 7, there's a couple of different ways that you can go about this. But one relatively nice way is to remember that the curl is given by a cross product. So if you wanted the curl of f plus g, this would be then the cross product between your del operator and the vector field f plus g, right? When you take the sum of these two vector fields. And you may recall, I hope that you do, back from 12.4, that products, like the cross product, obey a lot of your same product rules that you really like. In fact, it obeys pretty much all of them except for commutativity. So that is, one of them is a distributive law, that you can go ahead and distribute multiplication over addition, just like you do in your good old days. And so long as you keep your del operator on the left, because again, the order in which you multiply for cross products really matters. That so long as you keep it on the left, then this is true. This is equal. And so this is just the curl of f. This is just the curl of g. And so therefore you can add these together. Another way that you could, I mean, this is the most compelling argument I have that this is a true statement. Another thing that you could be thinking about is that curl is essentially derivatives, right? There's lots of derivatives going on, but curl is basically derivatives. And derivatives behave very nicely with addition, right? That you're allowed to take the derivative of one thing, then take the derivative of the other thing, and then add the results. So because curl is basically derivatives, right, that this is going to behave very nicely. In the same way that if this, instead of was curl, right, if it said div, that's also true, right? Div, divergence, is essentially a lot of derivatives. And so, or, right, you could also make this argument, but with a dot product. All right, this last one, I'll spoil for you, is going to be false. This talks about if you have two derivatives being equal, does that mean that your original functions had to be equal? Right? So divergence has a lot of derivatives in it. And we know even, right, if you start off with x squared plus 1 and x squared plus 5, that both of these have derivatives that are equal, and yet the original things are certainly not equal. And so that's why this one is going to be false. Just because two derivatives are equal does not mean that the original function has to be equal. If you want to formalize this, right, a counter example could be one vector field is x squared plus 1, and then you can just be zeros for the rest. And g could be x squared plus 5, and then zeros for the rest. When you calculate out the divergence of f, you're going to get 2x plus 0 plus 0. When you calculate out the divergence of g, you're going to get 2x plus 0 plus 0. Right? Take the derivative with respect to x of your first component, the derivative with respect to y of your second component, the derivative with respect to z of your third component, add those all together. Even though these divergences are the same, 2x in both cases, our vector fields that we started with are not the same. And so just because you have a couple of derivatives equal to one another does not mean that they came from the exact same function, right? These could certainly be off by constants. And when we have x's, y's, and z's, they could even be off by more than this, right? Because there's a lot of things constant with respect to x. You could really have any number of y's, any number of z's, all that sort of stuff. So, All right, that's the true-false problems here. As you can see, all of these fairly conceptual, but if you thought about these last couple in terms of derivatives, not too bad, not as difficult as 6, I think. So, all right, well, best of luck tomorrow on the exam. Of course, in the recitation, you'll have a review sheet to kind of help you review some of these things as well. And yeah, I'll stick around if there are any one-on-one questions.